Hello again, everybody. Welcome back to another episode of the Flocode Podcast. It's James here. Today I'm speaking with Peter Debney of Arup, another Arup guy, coincidentally. Ramis Hashan was the last guy from Arup that I spoke to. So, Peter is the author of the book Computational Engineering. It's available on the IStructE website. You can check out the links down below. This is a fantastic book, and it's one of my favorite engineering books that I think I've ever read, and it reminds me of the excellent On Structures and Why Things Don't Fall Down by J.E. Gordon. While it is focused on computational engineering, it covers so much more, and there are many different really helpful engineering isms. I don't know if that's a word, but that's what I'm using for it. And just these different ideas and quotes and concepts that will help you to think more clearly. And the way I would describe it is it's almost like you have the collective knowledge of, many different excellent engineers just narratively discussing a lot of the problems that we all face in engineering, which is basically how do we solve problems in the best way. So it does dive into the weeds in terms of, understanding parametric design and computational design and beyond. But sprinkled in and amongst all of this information is just really helpful general engineering ideas and concepts. So I really, really enjoyed the book. There's a lot of good gags in there. Some, Peter, they're not great, but I appreciate them nonetheless. And had a great chat with Peter. He has a lot of really interesting insights and has had a very interesting career that spans design and software development, and now he works on Oasis, which is Arup's structural design software. So great discussion. Check out Peter's book, highly recommend it, and I hope to talk to everybody soon. Be good. Bye-bye. Hello, everybody. Welcome back to another episode of the Flowcode Engineering Insights podcast. Today, I've got a guest, Peter Debney of Arup, and he is the author of a fantastic book, which we're going to talk about, and that is Computational Engineering. Peter, welcome aboard.
Thank you very much. Thank you, James.
So,
Glad to be here.
Well, I'm glad that you're glad, because so am I. Let's just briefly give the listeners a little bit of background about who Peter Debney is and what he does, and then we can take it from there.
Okay, so I'm a structural engineer by training. Originally a structural engineer who loved playing with computers, and now I more play with computers with a focus on structural engineering. So I work for Arup's digital development team, generally known as Oasis, because way back in the 70s, when Arup started selling software, you couldn't advertise as a consulting engineer. So they had to create a separate brand, which is called Oasis, which is Arup Systems. I've been working for them for 20 years as many, many roles, but mostly as a domain expert. I think that's safe to say. I'm also working with institutional structural engineers. So I am currently the Yorkshire Region Chair of the IStructE. I'm on their digital workflows and computational design. I always get the wrong way around.
It's a mouthful.
Yeah, I mean, it should be computational design and digital workflows. That's the way it should flow. But no, it's digital workflows and computational design panel. And I also am with Cross as a visiting expert. That is, I always get this wrong. I always think it's confidential reporting of structural safety, but maybe it used to be that. But anyway, it's a place where you report in things that have gone wrong, things that nearly gone wrong, safety issues, preferably things been caught beforehand. That's reported anonymously. Then the reports are written up. I'm there as a visiting expert on finite element analysis and computational design aspects.
Cool. That's interesting.
And
I didn't know about that one.
It's so I get involved when people have done silly things with computers, in
Like
engineering.
a
And
structural engineering watchdog.
let's try, yeah. I mean, the first one was um, somebody was designing a reinforced concrete flat slab or flat plate design building with a transfer slab at the first floor, or um, I'm trying to translate. It's yeah, the first level up. I know UK and American terminology varies, but anyway, there's transfer slab at the first level, and the engineer did the visual model, did all the structure in one go, analysed it, the whole thing was wished into place, and the reporter went, but construction sequencing, vitally important for concrete structures. Um, um, but also then the reporter then went, but the model's clearly wrong if we do that, because there's variable action happening, and that shouldn't be happening. But of course, flat slabs, they are statically indeterminate, so yes, there will be variable action happening. Um, so both the reporter and the original engineer got it wrong for slightly different reasons.
Hmm.
Um, and yeah, it was quite an interesting one to comment on that. And yeah, there's plenty that can go wrong with computers, and um, one of my jobs is helping people to avoid that problem.
And so for Oasis now, you're kind of the lead on dealing with clients, understanding what people want, how they use the
Yep,
software, that kind of stuff.
that's right. Yeah, so me and my team, we look after customer support, training courses, training materials, pre-sales for those who are thinking about becoming customers, but also then working with the development teams and sort of feeding client requirements into that, and working with the commercial teams, and we sort of sit amongst in between everybody, sharing knowledge in all directions.
So as is tradition, I always forget to ask my first question.
Mm.
And my first question is always, what is your life philosophy in a nutshell?
Uh, I think, I mean, bizarrely, it's the same as Arabs, um, which is well, the Arab phrase is building a better world. I've always just wanted to make the world a better place, um, and um, and over various levels. So making the world a better place, making engineering better for people, making engineering tools better for people, improving people's engineering knowledge. Yeah, just trying to improve things. Um, Optimization really, but optimization on the whole industry is the ambition. It's overly ambitious, perhaps, but
No, that's good.
uh,
Shoot for the stars. I
we'll do.
think we'll talk about it, but
Mm,
I think you've been hammering away quite successfully on that front. So
thank you.
um, okay, let's zoom out. The question I put to you is,
Mm,
what is computational design? How would you summarize computational design?
mm. So computational design, often conflated with parametric design, often conflated with engineering. I would say, so you've got parametric design where you're automating the digital workflow to create the designs,
Hmm.
but then with parameters which you can adjust and so on. But then computational design, you've got automatic feedback into that. So you're um, so you get the output out, which then feeds back in there, the optimization. What is the best section size? And it has to keep iterating till it gets there, or so on.
So
Um,
it's like the layer. So parametric design, you're dealing primarily with the geometry, and then
mhm,
computational design is now you have this layer of feedback. You have deflections and stresses and section
yeah,
sizes. So
yeah.
the calculations are occurring along with the geometry at the same time. Is
Mhm.
that kind of what you mean?
Exactly, yeah. And that might just be small things like section sizes, or it might be bigger ones like how deep should this truss actually be? And go find me how deep that trust should be, within the restrictions that the project puts on it. And then beyond that, there's computational engineering, which is whole system. Think about the scheme design, the detailed design, the CAD, the workflows throughout the whole project. And so, yeah, is that thought? So computational engineering is holistic. Computational design is that focus partly on the scheme stage, partly on the detail stage.
Yeah, I think, these terms are becoming more and more normalized. So
Mm,
I think it's helpful to sort of determine what we mean by both of them.
yeah.
Um, so you've had a long career in this field, and
Mhm.
it was previously very niche. Um,
Mm,
Nowadays, it's becoming a little bit more ubiquitous. Like, most young engineers are familiar with, at least with modeling programs and
mhm,
software, if not the underlying code behind it. So, how, like, in your opinion, if you were to talk to the next wave of graduating engineers,
mhm.
how would you tell them to think about computational engineering?
Mm, I would say think about it with a view on the end goal. I mean, there's a lot of techniques and so on which are fun and cool and interesting sounding. And it's good to investigate those. But the end goal is client delivery.
Hmm.
What does the client want? How can we deliver the best thing for the client? And that's the end goal. And I feel that this computational design is all about automating the boring stuff, easing the workflow, making your life easier, enable you to do better in the same amount of time, and and think on that. I mean, when you first start, there's always the temptation to go, oh, okay, genetic algorithms, they're cool. I'm going to do everything with genetic algorithms, regardless. And sometimes it's useful, sometimes not. But genetic algorithms aren't the end goal. It's delivery to the client,
Hmm.
and satisfying them
Yeah.
is the end. Yeah, and just how to get there quick as possible.
It's yeah, that you're right. That's the bottom line, is, like, we're in the service business, we're in the consulting
Mm,
service business. And what you've just said reminds me of a quote that I do some grappling, and there was a quote that a famous coach once said, that whereas, like, the highest level of black belts use very few techniques. So
mm,
the ultimate goal is to, use very little but be very good at it. However,
mhm,
to use a little, you have to know a lot,
yeah.
which I thought was it's, and engineering is the same way, where it's like,
Mm,
to be able to hone in and simplify things, you have to be able to, you have to have a broad knowledge to know
mm, yeah.
what's relevant, and that just takes time. I don't think there's a fast track to it.
I mean, it's a bit like the old adage of, if the only tool you have is a hammer, then every problem looks like a nail.
Yeah.
And a good engineer has a full toolbox of all sorts of techniques. And your grappling one reminds me. I once met a chap who was an Aikido expert, seventh Dan black belt, and he told me the best means of self defense is to be able to run faster than the other bloke.
Yeah. 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 Absolutely.
So lateral thinking is also good. So often, people come to me. Yeah, they got problems. So they come to me and said, "I want to do this," and I'm thinking, well, do you want to do that? What are you actually trying to do? What what does that step? What do you think that step is trying to achieve for you? So yeah, invariably then sort of digging back into, um, what is the underlying reason for that? And sometimes that is what they need, and but quite often actually no, they need to think, something slightly different. Uh,
it's such a fascinating topic, the topic of problem solving and logic.
Mm,
And what you just said is applicable to almost every domain. It's like,
yeah,
what exactly you're trying to solve, because the thing that you
yeah.
just said is like step one on a journey that you may not necessarily need to be taking.
Mm,
It's fascinating. And so I guess on that point, Peter, I'd like to just briefly talk about your book.
mm,
So computational engineering, I will put the link in the description underneath this episode. It's a fantastic book for engineers in general, and I don't mean just for people that are interested in computational engineering, but there is and I've spoken to you about this already personally, Peter.
mm,
I love the tone. It's a fun book. It makes me
mm,
enthusiastic about engineering and thinking about engineering.
mm,
And there are so many I've called them engineering isms, but I don't know what the right word
mm.
is. And they're like small pockets of advice that I just wish somebody would have told me as I was working and learning. And I would
Mm.
recommend to all engineers out there to look through this book, even if you don't care about computational design. Although, if you're listening to this podcast, you probably do. But there's just so much great value in there, and it helps you to think deeply, it helps you to think broadly. And yeah, there's just so many useful things in there beyond all of the real technical information about giving people advice on how to
Mm,
set up their finite element models, like common pitfalls, um, different ways that you can get your results to merge, or just the mindset that you should be thinking about as you're trying to do your digital engineering tasks. And none of
mhm,
this stuff is covered at a university level, in my
no.
experience. Did you ever, like, the stuff that you have in there is
Mm,
nothing that is really in any textbooks?
no. And I mean, I think the main reason.
Uh oh, we got frozen off. Peter, you back? Okay, you're good. We're still going. Sorry, you
Yes.
just dropped off after, just as I said, none of this
Mm,
stuff is in textbooks.
yeah, because one of the main reasons I started writing computational engineering was because I wanted to read it, and I've
What a
been looking everywhere.
laborious way to go about it.
I wanted to read this book, and I wanted to read it also when I was a new graduate as well,
Yeah.
and it wasn't out there, so I thought I've got to write it, and I was very inspired by um, the great J.E. Gordon, who wrote two engineering books, Structures, Why Buildings Stand Up, and New Science of Strong Materials, Why Buildings, well, Why You Don't Fall Through the Floor. And if you haven't read them,
Those are also brilliant books.
I love them. They got me through my degree. They inspired me. They showed me that engineering books could be interesting,
Yep.
which was utter revelation, and it's still quite a rarity.
Yeah.
And he talked about engineering, and he talked about his career, and he talked about asides and things. And so I was really inspired by him, and I wanted to produce a J.E. Gordon book, but for the computational aspects. And I must admit, I was also heavily inspired by people like Terry Pratchett,
Hmm.
hence all the footnotes.
Hmm.
If you ever read any of his books, and people like Douglas Adams and Lewis Carroll, or Charles Dobson, as is
Hmm.
known properly. Lewis Carroll, mathematics professor, and Douglas Adams, famous for Hitchhiker's Guide to the Galaxy. The more you read those with a technical eye, you realize how much computing wisdom is in there in both in those stories. And so, yeah, I wanted to share things which I thought were interesting,
Mm.
and also to slip in as many terrible engineering jokes as possible and see how many I could sneak past the editor. Most of them got through.
Yeah.
There's some of them are quite hidden. Because why should engineering books be boring? And 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 lots of pictures. Most books don't have enough pictures for my
It's
liking.
it's such a good book, but there's the other side of engineering, which is the complicated principles and the
Mm,
equations and the math. To learn that stuff, at least in my experience, I need to, like, it feels like I'm lifting a really heavy weight or something. My brain is
mhm,
just struggling to understand, like, I don't get it. What does this
yeah,
mean? And I
yeah,
have to, like, bang my head off it
mm,
again and again and try and look at it from multiple different ways. And then eventually, as like the small pieces consolidate, I start to develop an
mm,
understanding. But
yeah.
man, I feel like it doesn't come easy.
No, it doesn't. And so a friend of mine who has got a PhD in engineering maths, he told me once that people explain things using algorithms because they do not understand it.
Hmm.
Um, actually, the remit I was given was explain everything, but with an absolute minimum of maths. And so, in fact, there's only, apart from the appendix, there's only one chapter in there which actually has any maths in it, which is
Yeah,
the
I noticed that.
section on FE. What do the FE solvers actually do? Um, and Actually, that was the hardest one to write for me because, despite being sort of an FE expert for a long time, I didn't know how they worked. I'd always focused on the
And
end
if
result.
Peter,
Is it?
if you don't know how they work, like, what chance do the
I,
rest of us have?
well,
We're
I
building
knew
these things.
instinctively. I knew instinctively, and
Yeah,
also, you look, you get the model, and you go, do those results look right?
yeah,
And I was approaching from the engineering perspective. Is it giving me the right answers or not? And then I thought, and then and then okay, so I've actually got to dig into the maths. But dig into the maths, but try and make it as simple as possible. So, like all FE textbooks, I do cover static linear analysis, but just bars, axial only, because the principles of beams and 2D elements and so on is the same,
mm-hmm,
just more complicated.
mm-hmm.
So if you're interested in the more complicated bits, there's textbooks to cover that in depth. This is an overview giving you a basic understanding of what's going on.
Yeah.
And also noticed that all the textbooks sort of cover linear static analysis, but they never seem to mention P delta, nonlinear, modal dynamics, modal buckling, and that sort of thing. And I really wanted to cover all those again as simple as possible. Um,
The non-linearity and dynamics are, in my opinion, some of the trickiest concepts in engineering. So if
mm,
you ever decide to do a J.E. Gordon type book, I hope
mm.
that's your next topic.
Well, we are. Oh, I'm currently working on a new book with a friend on structural behavior,
Okay.
um, because one of the big dangers with computers is they will give you the answer, but you have to know before you do the model what the right answer is,
Yeah.
which is always a bit of a paradox. But so it's again those basics of structural behavior. Um, why do why do why do bending moments and shear forces always go together, and all these sort of things, and then sort of stuff. Then there's going to be some standard simple calculations for doing things. But um, if you want be a good to be good at dynamic analysis, what I found really useful is learn to play a musical instrument.
Mm-hmm. Yeah. Play
Um,
guitar.
yeah, guitar is brilliant for that, because you immediately know, okay, um, so the note you're hearing is the same as the natural frequency, um, and you change the length of the string, you shorten it, changes the pitch, change the frequency, you tighten it up, you change the stiffness, you change the frequency, you change the weight of the string, the mass, it changes the frequency. When you play a guitar and think of a building as a guitar, it's essentially the same thing. Also, of course, you do a modal analysis that just gives you the frequencies, and that is exactly the same as the guitar on its stand, just waiting to be played. Then you excite the strings by strumming or plucking or whatever, and then you get the dynamic response from the guitar, which is what the notes actually come out. And also you get the harmonics, which is the overtones, the coloration of the notes, which, if you're a guitar player, if you play different places on the string, it sounds different because the different harmonics that are coming through. And it is really, really useful.
That's a good analogy. So I guess we could briefly talk on, we talked about the difficulties of learning some of these complex ideas. What do you think about self-directed learning for engineers? Because the complaint is, you work all day. Where are you supposed to find the time to continue learning? In the case of your book, it's actually like an enjoyable read, which is, like you said, it's a rarity.
Yep.
So most of my learning has been kind of on the job, and then occasionally there's books that I like or there's courses that I'm interested in. But what are your thoughts on engineers and how that they should manage that kind of self-directed learning?
I mean, for me, as someone who I only discovered relatively recently is dyslexic, I actually struggled enormously through university, and didn't do very well at all. And dyslexia is sometimes described as a learning difficulty, but I think it's more difficulty with those forms of learning. For me, my engineering education really took off after graduating when I started self-teaching. Especially when preparing for the IStructE chartership exam. Self-teaching has been ideal for me. And that has been through books. It's been through magazines. It's been on the job, as you say. And especially in the early days, before the kids came along, working a bit late in the evening, experimenting with things, exploring things. Of course, in those days, it was all desktops, so you didn't have laptops you could take home.
Sorry, Peter. When you say that it was that you struggled a bit in university with the dyslexia, was it what were the biggest barriers? Was it the time that you had available, or the pressure of the assignments?
All of the above. I mean, in those days, we're talking 1980s. The lecturer would stand at the front and write stuff down on the blackboards, which you would then roll, and you had to copy. And the old joke about education is information going from the lecturer's notes to the student's notes without passing through the brains of either. I have terrible handwriting and terrible spelling. Really struggle to read my notes afterwards. And also, of course, you're supposed to sort of process them as you're going along, but you're too busy writing down. I think the worst one for me was definitely fluid mechanics, which was very equation heavy.
Yeah.
Didn't get that at all. Whereas some exercises we did, physical modeling exercises, doing cardboard bridge and a paper building and that sort of thing, and they were brilliant, and they really worked for me. Actually, I did very well surveying, but that's all geometry.
That's probably because you could conceptually map it out in your mind.
Yeah,
rather
very much
than
so.
dealing with like a wall of text.
Yeah. I've always been very good at picturing things in my mind.
Mm.
Um, 3D modeling, you do it in your head first, and then you either put it on paper or into the physical into computer model these days. But yeah, I could read. I never had much problem with reading. It was the writing and spelling, um,
And
which was
so
difficult, and of course the
what
workflows.
kind of like you said that you kind of blossomed a little bit more after you left university when you're kind of
Mm,
out of that, I don't know what you would call it. It's almost like an assembly line where you're just trying to get to the finish line.
mm,
But once you're out, what was it, were there any specific tools that you used or any kind of advice that you give to anybody out there that's kind of wrestling with the same type of stuff?
mm. I mean, for for me at that stage, it was the focus on the chartership exam, which
Did you just shoot for that as soon as you got out of university?
oh no, no, no. So I graduated in '89 and did the exam in '96.
Okay, so you had plenty of experience before
Plenty of
you.
time. Yeah, but it was broad experience. Sometimes job working on site, working in a small consultancy, working on for a big American petrochem contractor. Sometimes doing engineering, sometimes doing drawing. Sometimes I was leading a 3D CAD team in the mid '90s for a couple of years.
So let me jump into a slightly different topic here with you, Peter.
Mhm.
What is your own background in sort of programming languages, and like where did you start,
Mm,
and what kind of languages did you are you most familiar with, and if there are any that you use today?
mm. So, this it goes way back. So, the first computer I got my hands on was a ZX81 um, back in 1981,
I have
which
no
had
idea what that is.
okay, so a ZX81
I'm imagining
had
like
one.
a big lawnmower with like a
Um,
screen a big screen on
now
it.
actually, now this one was actually quite tiny. It was a weird. It was on the first home computers, and it was about the size of a book, and had 1K of memory,
Oh wow.
which you couldn't even put a text document into these days, and um, it was pretty hopeless. You can do you if to program in that you had to use machine code, and it was just um, it wasn't there. But then the year after, the ZX Spectrum came out, 16K of memory, and finally you could do interesting things like play games on it.
Um,
And
you've got two brilliant quotes at the beginning of your book. One is, "I think there's a world market for maybe 5 computers," from Thomas Watson, the president of IBM, and the other
yeah,
one was, "There is no reason anyone would want a computer in their home," from
yeah,
Ken Olson. So yeah, funny, leading experts at the
yeah.
time.
Uh, yeah, I mean, yeah, you had. I mean, those days you had to plug your tape player into the computer to load the program in, and it would go for about 5 minutes, and then go fail because you got the tone control slightly wrong, and you do it again. And yeah, so I started playing with that a bit. I at school, so I was yeah, so mid teenagers. So my year in school was the first year to have a computer in the school. um, so we had one computer for 30 of us, and started learning a little bit of assembly, but it was mostly basic. It was language where you had to put the line numbers in and
Mm.
use the dreaded go to command and everything. So did a little bit of basic programming, but if you got 30 kids all trying to type into the one computer, and nobody had home computers, or very few at those stages and everything, it was very difficult. I didn't get better for that. Then went to university. Fortran was the language of choice for engineers in those days.
Still is for some.
Mm. and um, yeah, so I used Fortran through university and doing a bit of FE analysis, though at that stage the Fortran was separate. I was using scripts to generate the FE models, but on the mainframe, which would then run for 24 hours before crashing.
When people say
Um,
mainframe, I always think of Star Trek. Um, because I've never heard
uh,
it. My generation has never heard of that kind of terminology.
it was basically there was a large room in the university which was full of computing gear, and we had the computer room outside where you could access terminals to connect into it and do your programs. And then the year after I left, they got rid of it and brought in PCs or
Mm-hmm.
the desktop machines. Um, um, did have a year out from university, well, sandwich year, working for a water company, and I helped introduce CAD into the company. Well, they were bringing CAD, and I was part one of the pioneers. That was on mini computers, and a mini computer was so called because it would fit under your desk. It was small enough.
You have an excellent. I'll also put a link to it, but you've got a fantastic article on the Sydney Opera House where you describe. It's kind of one of the first big projects to use finite element
Mm-hmm. Yeah.
analysis, and in there you mentioned the cost of running analyses back then,
Mm-hmm.
and it was
Yeah.
something like £5,000 a day or something.
I think it, it was more like £5,000 a run, which
Yeah,
could be about
£5,000 a run.
and yeah, and it filled the basement in the London office in those days. It was, but also to get onto it, you had to convince the computer group's guardians that that you knew what the model was going to be doing and how it was going to work and everything before you were allowed on. But yeah,
If that
it's
was still the case, Peter, I would be screwed because so much of the time I'm doing like exploratory stuff to
mm,
understand how structures are working, and I'm like
yeah,
changing supports, changing nodes, adjusting materials, and
mm,
I'm learning as I experiment how
yeah,
this thing is reacting. And if I was spending £5,000 every time I was trying to figure something out, like
yeah.
I wouldn't have yeah, I certainly wouldn't have any clients.
Mm. Yeah, I mean, I learnt a lot from just playing with the FE analysis over years and learning how things work, but also then separately really getting to understand structural behavior and so come at it from the two sides. And you got to do both. Anyway, computers. Yeah, so did Fortran at university. Really loved the CAD because I'd done engineering drawing at school, so I really loved the geometry, the drawing. Left university, 6 months on site, okay in the summer, terrible in the winter. Went into consultancy, FE analysis on the engineering computer. We had one for the engineers and two machines for the draftsmen, um, draft people, technicians these days, and that stage. AutoCAD. I think we can mention AutoCAD, can we? Or a well-known CAD program, which yeah, every time you started a new drawing, you had to set it all up, the parameters and everything. And I thought, oh, this is crazy. This should be automated. So I taught myself Lisp, which was the programming language required for CAD in those days, which is bizarre because it's actually an artificial intelligence language. Um, and it's a very weird one. We used to call it Lisp. We would say that Lisp stood for lost in stupid parentheses because everything was in brackets. Yeah, if you wanted to multiply two numbers, you didn't do like 5 times 3. You did times open bracket 5, comma 3 close bracket. And weird, very weird. But anyway, taught myself Lisp. automated the drawing setups, whilst also getting involved in 3D modeling in AutoCAD, which, considering it was really 2.5D, yeah, I mean, drawing's fun, but 3D modeling, that was more interesting. And this is early 90s.
Mm.
Then left there, went to Fleur Daniel as it was then, got into serious 3D modeling, which is all on Unix machines. So I got into a bit of C programming, to help keep the machines running, and optimization and batch plotting and goodness knows what else, that sort of
That's some
thing.
heavy lifting.
Then left there, joined CSC, the software company. My initial role was to turn a fabrication CAD program known as XSteel into a program for consulting engineers. That program has been rebranded. It's now known as IStructE.
Wow, I use Tekla.
And CSC and Tekla used to be partners. They were working together. Then they got divorced for whatever reason. So we'll then get involved with creating some 3D Plus, which went for a while, but then didn't get very far. Then CSC got bought up by Tekla, and Tekla bought up by Trimble, possibly in that order. But anyway, I left there. They ran out of money. Joined a small consultancy, but in the meantime, I was doing Open University self-teaching, Open University courses on computing.
Yep.
So I was learning Visual Basic, and also I did a object-oriented course. So I was learning Smalltalk, which is virtually unknown now. I think it was the first object-oriented language. In fact, it's 100% object-oriented. So if you want to learn that methodology, it's quite a good language for that. But and use that on the course really. But I did a lot of Visual Basic bits and pieces. Then left there, joined Arup in building engineering, back structural engineering, and then changed over to the Oasis team, and initially doing commercial sales and marketing and support, and then adding in training, and then adding in more technical things, and dropping the sales and the marketing and focusing on the fun stuff. And tried learning C++. Too difficult for me.
What's Oasis written in?
C++ mostly. Well, the desktop products are all written in C++ these days. The cloud programs tend to be more JavaScript, and yes, mostly JavaScript. Oh, I learned HTML. No, yeah, HTML, which sort of class programming language. And then discovered Python, which I thought, I like Python. Python's really easy. You can do a lot with Python. It's quite similar to Fortran, Basic, that sort of thing, similar syntax, but also, yeah, really good for just experimenting. I mean, why use a calculator when you've got a Python console you can fire up? Can't do everything. It not very good for interfaces, but yeah, Python's my go-to programming language these days, especially if you want to do something quick, good for experimentation. For producing something for somebody else, I should really go on to C#, but I haven't got around to learning that one yet.
I think
so. I've learned quite a language over the years.
I think the fundamentals of programming transfer perfectly a lot across all languages, and learning the syntax is kind of it's just a sort of a step in the process. It's a bit and it's becoming a lot less mind-numbing than it once was, because you've got all these AI tools now that can basically you're the problem solver, and if you can figure out the logic of how you want to solve your problem, you can just pick and choose the language that you want to write your functions or whatever in. Yeah, I agree. But Python is definitely my tool of choice for any and all engineering. But I'm not creating software like you are. You know, you've got like a commercial
mm,
software package that you're trying to get with a user interface you're trying to get people to use. Um,
mm,
so yeah, I understand why you need to think about the efficiency of your software, how it interacts with your machine.
mm,
But I'm a step down where I'm just trying to do engineering, and I think Python is the perfect tool for that.
mm. Yeah, I personally am not programming the software. We have a lot of people with great deal of experience doing the actual coding part, and and I gather you've been talking to one of my colleagues,
The Ramasashan.
Ramesh Session, yeah. He's leading our algorithms team, and we've got development teams. I sort of have some computing knowledge and some engineering knowledge, and then sort of joining the two together for the teams and acting as a sort of a guide. But um, yes, they do the programming. I mean, our GSA program, which is the fundamental analysis, I mean, it's got something like 2 million lines of code in there over about 60 different libraries. Um, yeah, it's intense. And yeah, it's you're dealing with FE analysis, which has got to analyze hundreds of thousands of elements. It's got to be as fast as possible, and C++ is very good at well, once you put the effort to get it working,
Yeah.
it is very, very efficient.
This is
Um,
this is a really interesting topic because most practicing engineers, they have enough on their plate. They're just trying to do their job. They don't
mm,
necessarily need to understand how the software works or why it works in the way
mm,
that it does. And
yeah.
so some people are interested, some people aren't. But
Mhm,
I always find it interesting to hear about, you know, the certain softwares that people like versus the ones that they don't like. And usually it's just a matter of, hey, this is what we use in our office. So this is the one that
mm,
I like because I don't have any choice.
yeah,
And
yeah.
in your experience, and I guess you're in a sensitive commercial position, but do you have opinions on any of the softwares out there, or would you prefer to avoid that topic?
Um, I am obligated to offer no opinions about our rival software. It is, yes. Um, we do what we do, and we try, and it's intended to be the best. If it's not the best yet, we're working on making it the best. Other programs are available. Um,
Fair enough. Fair enough. Um, okay, so going back to some of the guidance that's in your book. So you got a bunch of different sections. You've kind of got the first few chapters, which I really liked, were kind of more broadly about just
Mhm.
engineering in general and important
Yeah.
things to consider about scheme design or conceptual design,
Mm,
as people refer to it over here in North America.
yeah.
Um, and you also comment on the importance of diversity within a team and
Mm,
how, different ideas and stuff from different team members play a huge role. So maybe
mm,
just talk about that for a second. And also on your opinions about like creativity in engineering and just the broader concept of engineering itself, how you think about it. I really like some of
mm.
your perspectives in early in the book.
Yeah, I mean, if you think about your average building or bridge, or especially building projects, there has to be a huge diversity. There's the structure engineer, there's the architect, there's the M&E engineer, and so on. There's everyone's got their own perspective, their own specialism, and within the team, within your engineering team, you've got people. Um, there are people who are really, really good at scheme design. There are people who are really, really good at detail design. There are occasionally people who are good at both, but be honest, they're the exception, I think. You've got people who just do one thing, but the diversity comes in when you go, well, how about we, why don't we try this? Why don't we do that? Okay, we always do it in steel, but maybe concrete better, maybe timber will be better.
I love that. I
Wood
love that
wood
phase
mixture.
of a project. I love that stage.
Definitely, that's definitely our preference. I must admit, I'm one of the people who's much better at the scheme, the big picture stuff than the details. And
You have a great point in there about the naysayers. You know,
mm, yes, because that was a quote from I can't remember who it was. I was a graduate, attended a lecture up at the Institute of Structural Engineers. There was this old I can't remember, but he said, scheme stage, design, sky's the limit. You want open thinking, you want to explore the options, and there will be somebody in there who will just go, no, you can't do that because this, and you can't do that because of that, and everything. And his words were, get them out of the way, just give them a light flesh wound, to remove them, and you can you can explore all the ideas and come down to something, and then later on they are really really useful, really essential, because they will then their skepticism, I suppose, will then be really for good to actually hone design and make sure it does all work. And because even in the my team, or the Oasis company, we got people who are really really good at the technical stuff, but we don't let them near the product design to begin with, and so on. So I mean, stuff that very much fits in with the the design double diamond, which is, I think, it's a reasonably recent concept of that. Um, exploring the question first, really understanding the question, really understanding what the client wants, whatever, and then hone down to what you think is the answer, and then expanding into the solution of that problem, and the detailed design. And
I'm just going to
yeah,
share that. I'm just going to
um,
share that right now
mm,
on my screen because it's cool. You see it there,
mm,
Peter?
that's the one. Yep,
Yeah, just
that's the one.
walk us through that.
Okay, so initially you start with a problem, and there's the discovery phase, making sure you actually understand what the problem is. Answering the wrong question will never give you the right answer. Yeah, so often I'm working people and they say, here's a model, and then the question is, what is the question you are trying to answer? And they don't always know that. If you don't know the question, you don't know the answer. Anyway, so you discover what the problem, discover that what the question is,
Hmm.
then you define that in the way that you can address it. So you then hone down onto the design brief, the problem definition.
It's almost
What the
like what you described a moment ago, where initially you want everybody thinking broadly, so that's where
mm,
you consider everything. The more
yeah,
outrageous, the better. And then,
hmm yeah,
once you've kind of considered everything, then you begin to hone back in.
exactly. That full toolkit, and then working out which tools you need. Then after that, there's the developing and delivering. So developing, exploring the different answers to that problem, that defined problem, and then delivery, testing the different solutions, validation, checking, rejecting those that don't work, combine and improve those that do, until you have a solution that delivers to the client. Um, I mean, whilst I didn't realize at the time, when I was preparing for the chartership, for those who don't know, the IStructE chartership exam, you have 1 day to design a building or a bridge, and you have to come up with two distinctly different designs, and then say which one you're going to do some data calculations, do some drawings, write a letter or a construction sequence or something like that, and then after 7 hours, collapse in a small heap. Um,
Yeah.
um, and I remember reading a lot of the examiner's notes, and they say a lot of people fail because they only come up with one answer. Whereas you've got to come up with two schemes, and um, inspired by someone at university who did chemical engineering, and the first year chemical engineering, they had to come up with a book which contained every single chemical reaction. Thinking, how do you come up with every single chemical reaction? But they did. So I thought I'll do something similar for engineering. So I thought, right, what? So the main two things in structural engineering is crossing a horizontal gap and keeping something supported at height. Um, okay, so I tried to come up with a list of every single possible way of crossing a gap, horizontal structure, and every single possible way of a vertical structure. I never quite got to the end of it. There was still definite more things I could have done, but that exploration taught me there were so many different ways you could do something. So when I then went into the exam, I used that. I didn't realize at the time how many different ways could I solve this, and go, well, these options would work, those ones don't. So I sort of picking, choosing the bits which would work, and then combine them in slightly different combinations into two separate design schemes. One of which was really cool, and the other one which I knew that I could actually do the calculations for in the exam. That was the one I chose, because you always choose the one that you can actually do. Avoid that mistake.
But you know what?
So,
you know what's interesting though is like in the real world, you're not cut off from information. So if you have a good idea, you can make it work because you come up with your idea and then you would find the relevant resources and then you would make it work. But the exam is not set up like that. The exam doesn't test good ideas. It tests your ability to remember stuff and then do a calculation.
Interesting is an open book exam. You can take in as much documentation as you like.
But you've got a really restrictive time limit.
And the rule of thumb we were told was the more documentation you take in, the less chance you got of passing.
Yeah.
So part of that process was refining down to exactly the pieces of paper containing the essence of the information that I needed, and it's very much, that exam is all about knowing the answer and then demonstrating it, and I presume, and I've never seen it, I presume the professional engineering exams over your side are similar, but yeah, it's all about knowing the answer, and then I realized that having done a lot of exploration using FE analysis to understand structures, I was then going, okay, this is how the structure should work. I do the model and I prove it, I validate it, but also then gives us the detail and the actual numbers and that sort of thing. But I can look at what it's telling me and know whether it's good or not. Because I remember, yeah, I'm sure we've all had our senior engineers. You've taken your senior engineer to work, and I remember on the mind floor, he whole stack of drawings, whole stack of documentations, he just riffled through, finger went down, and said, "That's wrong." And how did you know it's wrong? And it's just, yeah, experience.
Yeah.
It's knowledge. It's knowing the answers up front. And the same way that these engineering directors can go to a site meeting despite not having been involved in the detailed calculations and still talk knowledgeably about the principles and the projects and everything, because they know what the answer should be.
Yeah, and honing in on what actually matters. Getting through all the padding and then asking, well, do we have the results? Is this verified?
Yeah.
So a question I have, kind of related, and this is kind of your advice for younger engineers out there, bridging the gaps between, engineering is a technical profession, but you're kind of only as good as your ability to communicate your work and your ideas.
Yeah.
or at least it's a very limiting factor. So what is your advice out there to younger engineers about, how they to think about? So you've got the technical stuff, you've got
hmm
the communication skills, the critical skills, the soft skills. What are your thoughts on that stuff?
Yeah, I mean, for me, as a lifetime stammerer, lifetime communication has always been quite forefront in my mind. There are many ways to communicate. One is through talking and writing, and one is through drawing and sketching. Both do them in parallel. Describe it, sketch it out. Especially if you're working with architects. Architects are very visually minded. Sketch something. This is what it's going to look like. Always remember from lessons learned. Emotional content in written language is very difficult to convey. Um,
Yep.
uh, so try to avoid it.
My wife could attest to that on
Mm.
many different occasions.
It's very easy to be misunderstood if you're not careful. So, you know,
Apparently,
keep
I'm
emotionality.
very sarcastic in text form.
It's easily done. Um, yes, and um, also a lesson in life. So it's the when you're in a hole, stop digging.
Easier said
You've
than
made a
done,
mistake.
Peter. Easier said than done.
Yeah. Oh yeah. But yeah, you made a mistake. You go. Ah, sorry.
I'll dig my way out.
um. Yeah. Um. I mean, also, yeah. So in general engineering, it's don't be afraid to stand in front of a room full of people. It is scary. I found it absolutely terrifying to begin with. But as always, it's look at things from their perspective. What do they need to know? What do they want to know? Um, how can you make it interesting? Um, 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 Certainly when it's come to presentations, look the people in the eye. Uh, don't look at the screen. Uh, look at the audience
Yeah.
and talk to them. Um,
Presentations are tough. Like I find sometimes, if I'm watching a presentation, I want the
mm,
person to do well. I want to enjoy the presentation. Like
mm,
I'm
yeah.
hoping for the best. I don't want the person to, like, I'm not judging anybody. I just want everybody to do well because that's in everyone's best
Yeah.
interest. But
Mm,
and I found that sometimes, not so much anymore, but there were times when if I was given presentations, I start listening to my own voice, and
mhm.
I'm like, what? How do I get out of this? I'm like trapped in this room, this echo chamber, and
Yeah.
I'm thinking about what I'm saying rather than just trying to deliver the presentation. Have you ever experienced that?
Mm. Oh gosh. One of the ways I've learned to deal with the stammer is to not listen to myself, but yet also at the same time, what been worrying really about what I'm going to say. Um, yes, what I'm going to say, the content of what I'm saying, rather than how I'm delivering it.
Mm. Yeah, yeah,
I
yeah.
mean, the how is important as well, but it's content. Content is king. I think was somebody once said. Um, yes, don't listen to yourself, and of course, as I know, you're going to be editing this later and listening.
Just make it, that'll be quite challenging trying to edit this without listening to it.
Listen to yourself is a terrible thing because do I really sound like that?
Yeah.
Yeah, we do. That's okay. We never hear ourselves the same way that other people do, and that's yes, a universal thing. Yeah, concentrate on the content, not on the not so much on the delivery.
So I
Um,
guess because we're running out of time here, that what I want to close off on is
mhm,
you have some great points about engineering in the future and all of the various
mm,
technologies and stuff that we can expect, but it's more about just a message that you have for those out there that are interested in computational
Mm.
engineering or perhaps
Yep.
intimidated by the subject? Because
Mm.
as we touched on, it's not really covered in university, or at least
No.
only at a very, very basic level. And
Mm.
in my experience, I found that the people that find success in this field are those that kind of have a natural interest and pursue it and kind of
Yeah.
make opportunities for this just happen.
Hmm.
So
Yeah.
what is your message to people that are interested in computational engineering? And my first point would be read Peter's book, because it really gives you a fantastic foundation in everything that you need to consider
Hmm.
for a foundation for computational engineering.
I mean, for me, it's follow what's you find interesting. Not everybody will do computational design. Not everybody will be on site. It's a specialism. I mean, I would recommend everyone to do a bit of programming, a bit of automation, because that helps, and it also helps you think through breaking things down. But
That's
yeah,
actually
it's
that's a
just
brilliant point. And even if you don't use it in your day to day practice,
mm,
the mental gymnastics of deconstructing a problem
mm,
into a sort of a logical sequence. It's basically just a flow
yeah,
chart of
mm,
if it's
yeah,
this, if this, then that, and you just work your way
mm,
down. Yeah, it's a great
yeah,
point.
yeah. It's yeah. If you're interested in it, um, get hold of a copy of the Python or Grasshopper or whatever it is, and start playing. Well, I set yourself challenges. Go, how can I do X? How can I do Y? Um, some of it will be useful, some of it won't. But explore and experiments. Um, um, do things. Yeah, if you're interested in things outside engineering, go for that. I mean, one of the first 3D CAD models I made was of a stage set. My wife had designed a stage set for the local amateur production, and she come up with some concept drawings. I built a 3D CAD model of it. Did I need a 3D CAD model? No, but it was a fun way of exploring ideas, getting practice,
Yeah,
and producing something useful at the end. Um, yeah, not everything has to be useful, but look, things. Yeah, if it's fun, you're more likely to explore it, and
absolutely.
then what you learn can then be applied later on.
Yeah, and you never know how it will be useful later.
Mm,
The
no,
concepts are so transferable that if you pick a problem, like it could be a personal thing that you're trying to do at home, a DIY project,
mm,
you learn the basics, and you never know how useful or transferable that those skills will be down the line.
no,
So
no. Mm,
to close things off,
mm,
I will provide the links for everybody. Thank you so much for the discussion, Peter. It was really interesting getting your perspective on just a broader picture of computational engineering, as
mhm,
well as just your thoughts on the industry and your own career. And for anyone that's interested in learning more about Peter's journey through engineering, he has a great speech from IStructE that's on, I think it's on the IStructE YouTube channel. I'll link that down below as
mhm.
well. And people can check that out too. So, any closing thoughts, Peter?
Oh, many. Um, but yeah, um, yeah, engineering can be fun. It can be terrible, but it can be fun.
Both
And
things can be true.
um, yeah. Um, I mean, some people have a definite career path. I just follow my nose of what looked interesting. And um, uh, for those people out there, like now, I mean, this job that I'm in now did not exist when I graduated 30 years ago, and there's no way I could have set up a career path to get to where I am today. And in 30 years' time, who knows what job opportunities will be there for the engineers. Things change, technology change. I mean, when I graduated, say not only were the computers just about fitting under desks, but um, the concept of having one fitting into your pocket was unknown.
Mm.
The internet was invented 3 years after I graduated. Now, well, we couldn't be talking now,
Yep.
however many thousands of miles we are apart. Um, what's technology going to be like in 30 years' time? We don't know. But it's going to be fun finding out. Be flexible.
Yeah.
Explore.
Yeah. And I think, yeah, you hit the nail on the head. And just be aware of how the shifting sands are changing, because already the
Mm,
last couple of years, AI has already had a big impact,
mm,
and that's only going to grow exponentially, I think, for good or for bad,
mm.
remains to be seen.
Yeah, but also, I'm pretty sure we're just about to hit another AI technology. You get that hype cycle, and I think AI, in particular machine learning, we're on a sort of approaching a peak hype at the moment. There's going to be a crash, and then people will work out what we actually do with it, which is useful. And AI and technology has had this hype, crash, useful cycle throughout the years. To extent, actually, we're actually using quite a lot of um, AI things already, and have been doing for decades. It's just we haven't realized it because it's been really, really useful.
Mm.
Um, I'll talk about some of those other talks. I mean, one of the earliest AI tools, which I've always found very useful, grammar checkers.
Mm.
Grammar checkers on your word processor is an AI application derived from natural language processing. Um, internet search, searching through an unsorted database, it's an AI application. That's why Google is one of the leaders in AI, because it's been an AI company since the 90s. Your sat nav is an AI application. It's not machine learning. I mean, people think machine learning is AI. Well, machine learning is a subset of AI.
Hmm.
AI is a huge topic, and people experimenting with Chat GPT and so on. And there's a few possibilities, and I think in a few years' time, people are going to come up with the killer applications for it. Um, we're still at the exploratory stage at the moment,
Yeah.
and um,
It reminds me of, when there was a cryptocurrency phase there a few years ago.
mm,
People were trying to figure out how to fit blockchain into, bridge design
everything.
contracts, and, how
Mm,
can we do a blockchain? And it was just
mm,
hype. A lot of it was hype. It's like,
yeah,
this is
yeah.
unnecessary.
Yeah, I mean, as there's a thing about technology where when you're child up to about 15, all technology is just a natural part. New technology, natural part of life.
Mm,
From about 15 to about 30, new technology is innovation and exciting. And after you're 30 or 40 or whatever it is, new technology is the work of the devil.
interesting.
Uh, and but for me, almost all technology still is exciting and innovative, apart from Bitcoin, which I've never liked. And it always seemed like a giant Ponzi scheme. So who knows? Blockchain itself might eventually be useful. Bitcoin, no,
Who
um,
knows?
can't see that going anywhere still. But anyway, yes,
You
embrace
trust
technology.
you fully trust the U.S. Federal Reserve.
I fully do not trust my own skills at not losing passwords, um, or keep everything on the hard disk. And the older hard disk has died. And now what? And where was that piece of paper that I stashed? With who know? No. Um, there are people out there who are better at me at securing bank accounts. And
Yeah.
but maybe if you are super organized and high security and very, very careful at keeping track of those things, then maybe it could work for you.
Yeah.
It's not for me.
Yeah. Okay. Well, thank
Mm.
you very much for your time, Peter. And I
Pleasure,
wish you all
James.
the best. And hopefully we'll talk
Thank you.
again sometime in the future.
That'd be great. I look forward to that. Thank you very much.